seen this before? So the problem is H is the orthocenter of triangle ABC and A prime, B prime, C prime are the antipodes. That means the diametrically opposite points of ABC in the circumcircle. So yeah, I am speaking. If there's an issue that must probably be on your side. So let me introduce the circumcenter. So A prime is the reflection of A in the circumcenter, and that's what it means to be diametrically opposite. Okay, then what you do is you reflect A prime on BC, B prime about CA, and C prime about AB to get points X, Y, and Z. And they are marked in yellow. So problem asks us to show that H, X, Y, and Z are cyclic, concyclic. So this is a little bit strange because how do you relate X and Y? They are defined kind of differently. Like I mean, it's the reflection of B over AC and A prime over BC. Any ideas? Mm, Uh, any ideas? Uh, yeah, A prime is the reflection of H over the midpoint of BC. Good. So let's call the midpoint of BC as M sub A. Then A prime is the reflection of H over M sub A. So yes, Samarth says introduce the centroid. So you know what? I'll actually give a really nice hint. It's there in the diagram itself. So can you make a conjecture about H, X, Y, and Z? Yeah, I'm not introducing the centroid now. So actually, can you make a nice conjecture about H, X, Y, and Z? It's there in the diagram. So we want to show they are concyclic. Okay, just stare at the diagram for a few seconds. Yeah, HX parallel to BC, that's pretty obvious, right? So if you reflect H about BC, you get another point on the circumcircle, HA. Okay, and we know that HA prime is parallel to BC, correct? Yeah. Uh, so it will be better if you people speak up. So anyway, HA prime is parallel to BC. Then since H is the orthocenter, the angle between AH and BC is an right angle. Correct? No, in fact, since X is the reflection of A prime, A prime X is perpendicular to BC. Correct?
Yes.
I mean, yeah,
Right.
nobody is speaking up. Yeah, okay, good. So now because A prime HA is parallel to BC, the angles HA prime and X A prime H sub A are 90, correct?
Yes.
Yes.
Yeah. And because they are parallel, yeah, let's call the foot of the A altitude D and the other point D prime. Okay, so because HA prime is parallel to BC, we can conclude HAD is equal to A prime D prime, correct? These two lengths are equivalent. I mean, that's just because they are parallel, right? The distances between the lines are equal.
Correct.
Correct. Now, H is the reflection. So H is the reflection of H about BC. So HD is also equal to DH prime, right? DHA. Yeah, right?
Yes. Yes.
Yeah,
Wait, could you repeat?
yeah,
Could
okay.
you repeat the
So
last statement?
HA is the reflection of HA is the reflection of H on BC. So
Correct.
HD equals HAD, correct?
Yes.
The HAD equals A prime D prime, right?
Yeah.
A prime D prime equals X D prime.
Correct.
Correct. Now, what can you say about the quadrilateral HX A prime HA? Yeah,
Rectangle.
it's a rectangle. Good. That's because, again, yeah, these two are equal. So this must be parallel to HX is parallel to BC. And yeah, one of the angles of that quadrilateral is 90 degrees. So it must be a rectangle. That makes sense?
Yes.
Yes.
So for now, we'll remove Y and Z from the picture. I mean, they're not doing anything. Okay. Now, if you drop a perpendicular from O to HA prime, what is this point?
Midpoint.
No, this is the midpoint of HA prime, correct?
Mm,
But then
Yes.
the quadrilateral HXA prime HA is a rectangle. So what can you say about this point? The point
It's
here.
also uh,
That's a
it's
midpoint
also
of HX,
midpoint also.
HX, right? So if it's the midpoint of HX, what can you conclude? The perpendicular from O to HX bisects HX. So that means
H equal to X.
OH is equal to OX.
Oh,
Yeah, can you I mean, can you complete the proof now? Again, by similar argument, OH is equal to OY and OH is equal to OZ. Correct?
yes.
Correct?
Right.
Yeah.
Yeah.
Right.
Right.
So that must mean H, X, Y, and Z lie on a circle centered at O. Correct?
Yeah.
Correct.
Yeah, so that completes the proof. Now, what I want to do is I want to generalize this question. So first, we realize that the points A prime, B prime, and C prime are dependent on a point O, correct? And the triangle ABC, of course. Okay. Um, so if we were to replace this point O by another general point, let's say P, I'll write here. So here's a point P. Now, how can you generalize this point A prime? Yeah, so if you join now, just take a screenshot of this problem. So I just solved this one and I'm trying to generalize this.
Yeah. Okay. Done.
Yeah.
Done.
So instead of O, I'm taking another point P. So in what ways can you generalize these points A prime? So again, I have two ways of generalizing. A prime is the intersection of AP with the circumcircle, or Another way of generalizing is A prime is the reflection of A over P. Okay, both of these coincide in the case of circumcenter, but in general, they are not the same. So, for example, let's take the circumcircle case. So, this is A prime. Again, we define B prime, C prime similarly. So, again, X, Y, Z are reflections of A prime, B prime, C prime over B, C, C, A, B, respectively. So, Y and Z. So, in this case, in the circumcircle case, it turns out that X, Y, Z, H are concyclic. So this is called the Hague circle of P. And now I'm not going to deal with this one in this lecture. So we'll actually generalize it in this path. So in this path, what happens is, just a minute. I'm taking a triangle ABC and some point P, reflecting A over P to a point A prime. I'm sorry again for my poor diagrams. B prime, C over P to B, C prime. Okay, so if you reflect A over BC to point X, B over CA to some point Y, and C over AB to some point Z. So in this case, it turns out that XYZ has circumcenter O. Circumcenter coinciding with coinciding with the circumcenter of ABC. So if O is the circumcenter of ABC, then O is the circumcenter of XYZ. So I'm going to leave this as an exercise. Hopefully you will be able to solve it after this lecture. Okay. So are there any issues till now?
No.
No. Okay, good. So we'll begin with Miquel points. Again, take a triangle ABC. Oh, sorry about that. So let D, E, F be 3 points on BC, CA, and AB. So the circumcircles are triangles AEF, triangle BFD, and triangle CDE are concurrent. Can you give me a short proof of this?
Yeah, like just draw the circles. That would
Yeah,
be a
I'll
good.
draw the circumcircle.
Assume like one point is the intersection of two circles, then angle Z.
Yeah, so angle chase. Let's call this point P. So again, I'm going to do this for the special case. I mean, special case of P inside the triangle. In general, you can use directed angles to solve. So this diagram is pretty easy to work with. So if you extend FP slightly, I'll remove P for now. Now, because of the cyclic nature of quadrilaterals AFPE, these two angles are equal, right? Let's color code them. Oh, yeah, these two are equal. And one more, this angle and this angle, right? Does that make sense? Yeah, sorry, I'll just
Yes.
Yes,
yeah,
yes.
and
All right.
yeah, so the angle C and this angle add up to 180 degrees. So that must mean C D P E is cyclic. Okay. So this point P is called the Miquel point of triangle DEF with respect to triangle APC. Okay. And so now what I'm trying to now what I'll do is again taking a triangle ABC, I'll take F here and some point E here, and see again you have to note that D is independent of E and F. That means I can move D along BC without, I mean, and still the concurrence of the circles will hold, right?
Okay.
Yeah,
Uh,
because the point is on the line, not on the segment.
Sorry. So no. What
Yeah,
I'm
like
trying to,
because
huh?
yeah,
Yeah.
and
Go ahead.
like you said, D is on the line, so D can be
Yeah, D
outside
is on the
BC.
line and it's independent of the location of E and F. So now if I move D along BC, yeah. One more thing is you can note that it need not lie on the segment. It can go over. So D can go here or here, and the result of concurrence will be true. And then for that you can just you use directed angles to generalize this argument, right? So now if I move D to this special location of EF intersection BC, what happens? Again the concurrence must hold, right?
Yes.
Yeah.
Right.
So let's call the concurrence point M. So it will be, I don't know, somewhere here.
Yes.
So now what I'll do is I'll look at M from a different perspective, the perspective of triangle BFD. And we look at points A, D, E as on sides of the triangle BFD. Okay? So yeah, just a minute. Let me confirm. M is the common point of triangle AFE, DCE, and BFD. Now, if I look at it from the perspective of triangle BFD, yeah, this one, and we look at AE and C as uh, points on the sides, and again by this result, previous result, we see that triangle, the circumcircles of AFE, uh, DEC, this one, this triangle, and ABC are concurrent, right? Or did I confuse you?
Could you repeat it once?
Yes, yeah. Can you repeat, please?
Yeah, you want me to repeat? Oh, okay. Rather, we'll go by a different argument. So if EFD are collinear, can you show that M lies on circumcircle of ABC? So again, yeah, M is the intersection of circumcircles of AFE, CDE, and BFD. Okay.
So it will be the common point for it on the circle.
Yeah, I'm asking you to show
Yeah.
that M lies on the circumcircle.
By spiral symmetry will be done.
Spiral similarity. I don't want to go into that, and I don't think that will give the result either. So anyway, it should be simple angle chase, right? So angle AFE
Yeah, like
equals
how come it is spiral symmetry? Yeah,
uh,
angle chase would do it.
yeah,
Just
angle chase will do it. Yeah. So you know what? I leave it as an exercise. This should be pretty simple. Okay.
yeah. All right.
Yeah. So just a moment. Yeah. So what we have in the table is, if you have 4 lines, we can see that. Yeah. So the 4 lines here are AFB, AEC, BCD, and DEF. Okay. So in general, for 4 lines, the circumcircles of the triangles formed by 3 of them at a time will concur at a point. So that is this circle, this one, mm, this one, and this one. And they all concur at a point, and this thing is called the Miquel point of these 4 lines. Okay.
Yeah, got it.
Okay.
Yeah.
So yeah, now we'll go into something called Simpson lines. So once again, we have a triangle ABC and some point P. Okay, so for now, let's not impose any conditions on P. Okay, then you draw perpendiculars from P on the 3 sides. Yeah, let's call this, yeah, D, E, and F. Okay, so I want you to show that D, E, F collinear if and only if P lies on circumcircle of ABC. So any ideas? Yeah, I'll just give you a hint actually. Most
CD
of
is
the
concyclic.
setting. Yeah, sorry.
So CDP is concyclic, and similarly PE
Yeah,
is
yeah.
concyclic.
Okay. So some cyclic quadrilateral C, D, E, P. And what else? A, E, P, F. And there's one more. B, D, P, F. Right? Yeah, so the thing is, I'm not doing any spiral similarity or advanced stuff right now. Okay. And so DEF collinear, what does that mean? I
like
mean, okay.
we
Yeah,
can there are a bunch of right
angle
triangles.
condition.
So,
Yeah, bunch
so like
of, yeah,
we
correct.
can we see that what is this PEDC is a cyclic.
Yeah, these three are cyclic.
Yeah.
So again, DEF collinear is just an angle condition. So I'm going to use directed angles right now. So DEF collinear if and only if directed angle, again mod 180 degrees, FEA equals directed angle DEC. Does that make sense?
Yes.
DEC is this angle,
Yes.
and FEA is this angle. Okay. So if these two are equal, only then DEF is collinear. DEF are collinear, and if DEF are collinear, then these two angles are equal. So again, that's an if and only if condition, right?
Yes.
Now angle DEC is equal to angle DPC, right? Because of consequence. Okay.
Yes.
I'll just draw
Oh,
angle
oh,
DPC.
yes.
Okay. And then angle FEA is equal to, oh, this is not visible. FEA equals angle FPA, right? And does that make sense? Again, because of Cyclic. Now, angle FPA equals angle DPC if and only if angle FPD equals angle APC, right? I'm just going to add this angle. I'm just adding angle APD to both.
Yeah.
Yeah, that makes sense, right?
Yes.
Okay, so now what is angle FPD? If we isolate FPD from this diagram, FPD, and there's a point B. How is angle DEC equal to DPC? Oh, that's because this triangle is this quadrilateral is cyclic. DEC and DPC. I'll just draw the circle for you. Yeah. So from the diagram in this corner, left side corner, we see that FPD equals angle FBD, right?
Yes.
Yeah. So if FBD equals angle APC, what does that mean? I mean, angle FBD is equal to angle ABC, right? I mean, they're the same angle. FBD and ABC are the same angle. Okay.
Yes.
So
Yes.
so what we have is this thing. Angle APC is equal to angle ABC, which means P lies on. I'm using this notation. So this means circumcircle of ABC. Okay.
Okay.
Yes.
Okay, fine.
Yes. So this whole quadrilateral will be a cyclic if P lies on the circumcircle.
Yeah, P lies on the circumcircle. Yeah, sorry for
Okay.
the poor diagram, but once again, um, if P lies on the circumcircle, this line is called the Simpson line of P. And yeah, one more point there. This line is known as the Simpson line of P. And this is a interesting object. So it satisfies a few properties. So first thing is, if you extend this perpendicular to some point, yeah, let's name these points DEF. So if we extend this one to a point, say PA, so first thing is APA is parallel to Simpson line. How would you show this?
What do we have to show? Can you repeat?
because P
Angle AP.
Sorry, so we are trying to show. Yeah, 1 minute, 1 minute.
is like a reflection of A.
It's not any. Just a moment. Yeah, we are trying to show that the red lines are parallel.
Okay,
Okay.
okay.
Can I tell?
So, yeah, sure. Go ahead.
Angle APAP
Yeah, this angle. Let's use directed
is equal
angles.
to angle ACP is equal to angle ECP is equal to angle EDP because EDCP is cyclic.
Yeah. Correct. So angle APAP is equal to angle ACP, and that's because the quadrilateral APCPA cyclic, right? So this angle right here and this angle right here are equal, right? Now you look at this quadrilateral PEDC. So this white angle now jumps to this one, and these two are equal. And are you able to follow?
And now say now
Yeah.
and these two lines are parallel. F.
Yeah.
What is this?
So,
F,
so
the
DEF and
corresponding angle.
APM. Yeah, sorry.
Yeah. AP
Oh,
and
what?
F, and then what is that point?
Which point?
FD. FD and AP are parallel.
Yeah, that's all. So DEF and APA make same angle with the line. Yeah, I'll just write that down. Okay. So that means DEF and APA are parallel. Okay, next exercise. So one thing is this is a powerful result. It will be better if you remember it. Okay, next thing is angle between Simpson line of Simpson line of P and Simpson line of Q is equal to angle between in general angle PAQ or angle PBQ, all are equal. Okay. So shall I draw Q on the same diagram or will it confuse you? So like this. Okay, I'll rather not draw
No,
this.
it will be fine.
It will be fine. Okay, fine. And you know what? I'm not drawing the Simpson line of Q. What do we know about the Simpson line of Q? We just saw this result that if you take the projection and extend it to some point QA, what do we know? Uh, we know that AQA is parallel to the Simpson line of Q, right?
Yes.
Yeah. So
Yeah.
the angle between Simpson line of P and Q is same as the angle between the red and the yellow line, right? I mean, because the red line is parallel to the Simpson line of P and the yellow line is parallel to the Simpson line of Q. Does that make sense?
Yeah, got it.
Can you please repeat?
Yeah, so we just saw that the red line is parallel to the Simpson line of P, right?
Yes.
And now if you take a point Q and you define QA similar to the way you define PA, then
Yeah.
the yellow line is parallel to the Simpson line of Q, correct? Yeah, okay. So that means the angle between Simpson line of P and Q is same as the angle between the yellow and the red line, correct?
Right.
Yeah. So the angle between the red and the yellow line is actually very easy to evaluate because QQA and PPA are perpendicular to BC, correct? So they must be parallel. I mean, sorry, PQ and PAQA must be equal. So let me write that down. PPAQA, Q is cyclic and PPA is parallel to QQA. So that means that quadrilateral is an isosceles trapezoid. Correct?
Yeah.
Yeah, so wait. If it's going over your head for a second. So if you take two parallel lines, then what I'm saying is these two lengths are equal. Okay?
Yeah.
And does that make sense?
Yeah. Makes sense.
Yeah,
Because
okay.
the perpendicular distance between these two lines will also be always be equal.
Yeah.
So
Yeah.
these arcs are
Yeah, these arcs are equal. So if these arcs are equal, then the angle subtended by PAQA will be the same as the angle subtended by PNQ. Right? So what that means is, I'll write it here. Angle PAAQA equals angle QAP. Right? This one.
Yeah, got it.
Yeah, so this one is the angle between the red and the yellow line. So that's the angle between the Simpson lines. And this one is just dependent on P and Q. So angle between Simpson line has a really nice expression. Okay. So I was thinking, yeah, next thing is Simpson line. And so one more thing is H is the orthocenter of ABC. Let's call H the orthocenter of ABC.
Simpson
Okay.
line bisects PH.
Yeah, Simpson line bisects PH. PH. So what that means is in this diagram, PH is uh, bisected by the first red line. Okay, wait. I'll make a new one. So let's call this P. Somewhere H. So Simpson line bisects PH. So this property, I don't think we have much time in it. So I'll leave it as an exercise. Again, if you are stuck on this, then you can just Google it or refer some standard textbooks. It should be there. So now we'll do two problems. Okay. So the first one is AoPS, from AoPS. So wait, let's take a triangle and ABC and circumcircle gamma, and circumcenter O. Now the reflection of A in O is P, and D lies on BC so that AD is perpendicular to BC. G is the centroid of ABC. So I don't know, let's call it G. The ray GD meets gamma again the point Q. Show that PQ, BC and the tangent to A. So okay, this is gamma. The tangent to A, tangent at A to gamma, PQ and BC are concurrent. So you have to show that. So I'll give you time to think about this problem till I complete writing down the problem. Okay.
Yeah, okay.
Yeah, once again, ABC is acute and scaling.
Can you just repeat what we have to prove?
You're supposed to show that PQ, BC, and the tangent to A at gamma, tangent at A to gamma are concurrent. Yeah, I've completed writing the problem, so shall I proceed to the solution? Or rather, I'll try to motivate the solution. So first, if you look at the points, almost all of them seem related to uh, relevant, and just one point seems off. Which one is that?
There is D, the
Yeah,
90 degree, and
yeah, there's a 90-degree. Yeah, one point seems off. Like it's not
E.
relevant. Yeah, the point G. Yeah, G is the centroid and it comes from some midpoints and lengths. And
Yeah,
here we are dealing with angles and stuff. So G seems off. So can you think of a replacement of some sort? Or rather, how do you eliminate G from this picture? I mean, rather than just erasing it. Yeah, okay, I'll give you a hint. Actually, the figure is not very accurate. Just a moment. So, how do you eliminate G? Any ideas? So, I'll actually tell it. Do you know anything about this point? Let's call that A prime. Again, so forget about P and Q and other stuff. Uh, Forget about P, Q, etc. Just focus on G and D. Can you say something about A prime? A prime is parallel to BC. That's right. A prime is parallel to BC. So anybody with a short proof of this? G is the centroid. We haven't used that yet. So just a moment. AD is perpendicular to BC and G is the centroid. Okay, let me ask you another question. What happens when you dilate, circumcircle, about centroid with ratio -1/2. What happens?
Q maps to D.
No. Q doesn't map to D.
Yeah,
A
no, no.
prime maps to D. See,
Yeah,
because Q is on ray GD and A prime is not on ray GD. It's the other
yeah,
side, and we are taking a negative ratio. So
yeah. My negative, right?
yeah, so A prime goes to D, but A goes to what? A goes to midpoint of BC, right?
Mm-hmm. Yeah.
A goes to midpoint of BC. B goes to midpoint of CA. C goes to midpoint of AB. So circumcircle goes to 9-point circle, correct? See, because circumcircle of
Yeah,
the triangle
yeah,
formed by
yeah.
midpoints is 9-point circle, correct?
But I guess this is a bit strange.
And that's a
So
bit
that
strange, right? Yeah, okay. Or if you are, I don't know how else to motivate this, but yeah,
no, no,
probably.
homotheity thing is right. Homotheity is like a bit motivated because there is a floating ortho centroid. We can think of homotheity.
Yeah. So the thing is, in general, when there's a foot of perpendicular and centroid, you kind of automatically construct this point A prime. Okay, so just think of it like homotheity at G and ratio -half. Take circumcircle to the 9-point circle. Agreed? Yeah, that's because ABC go to the midpoints, and the circumcircle of ABC goes to the circumcircle of triangle formed by midpoints. And the circumcircle of triangle formed by midpoints is the 9-point circle. Correct? Am I making sense here? So no response. Yeah, okay, fine. At least one. So now we also know that D lies on the 9-point circle, right?
Yeah.
So if D lies on the 9-point circle, then the inverse image of D should lie on the circumcircle. That's precisely A prime. Okay. So that means A prime is parallel to DMA and is equal to twice of DMA.
Mm. Right.
That, yeah, that should make sense.
Yeah, yeah, clear.
Yeah, so now you can safely remove G from this picture. Now A prime is parallel to BC. If A prime is parallel to BC and AP is a diameter, so A prime P angle is 90, correct?
Yes.
If A prime P is 90, then A prime P is perpendicular to BC. Does that make sense? Yeah, I'm sorry for the bad diagram once again. Please bear with me. So let's call this point, yeah, give me a name. Let's call this R, intersection of A prime P and BC. And A prime P is perpendicular to BC because A prime is parallel to BC. Now, in this diagram, we have a lot of perpendiculars, right? Yeah, oh yeah, one more thing is AP is a diameter, so AQP is also 90, correct? Let me just do this. I'll just remove over. It's just an eye. So, am I making sense here? Everything all right?
Yeah, yeah, all right.
Yeah, okay, so we have a lot of perpendiculars. I'm just marking them with color. Sorry. Yeah, so if you look at this, kind of reminds me of something called the Simpson line. The points Q, D, and
Yes.
A prime are collinear, and they are all associated to the point A with some right angles, correct?
Yeah. Yeah. The Simpson line of A.
Simpson line of A with respect to what triangle?
Uh,
Simpson line of
like,
A.
like this is what triangle you ask?
Yeah, what's the triangle? I mean, you look at the other three sides, obviously. With respect to triangle formed by, yeah, it's not in the picture actually. Formed by PQ.
Yeah. Yeah. It's not in the picture, I guess.
Yeah, the triangle formed by PQ, PA prime, and BC. Correct?
Okay.
And does that make sense? Yeah, because Q is the perpendicular to PQ.
Yeah. Yeah. We can extend. Yeah. Makes sense.
It's the perpendicular to BC, and it's the perpendicular to PA prime.
Yes.
And so now we see that the intersection of PQ and BC comes naturally as one of the vertex of this triangle. There's a PQ here and there's a BC here. Okay, and we want to show that the tangent at A also meets at this point. So if you call the intersection of these two as S, then QDA prime is the Simpson line of A with respect to what triangle? Now it's there in the picture. Yeah, I'll tell you. It's triangle PRS. If you look at it, D is the foot of the perpendicular from A onto
Yeah.
RS.
Yeah. Like if we extend PR, we see that it is perpendicular at what is that point?
Yeah, A
Like,
prime. Oh,
yeah, A
sorry,
prime.
sorry, sorry about that. A
Yeah,
prime.
yeah, yeah. So that triangle
So,
PRS.
yeah, the feet of perpendicular are collinear. That must mean that A lies on the circumcircle of PRS, correct?
Yes, correct.
Yeah, if it lies on the circumcircle of PRS, then some angle condition. And one angle of PRS is 90, correct? This one.
Mm.
If angle PRS is 90, then angle PAS should also be 90 because A lies on the circumcircle.
Okay.
Yeah. So if A lies on the circumcircle, this is 90. But
Yeah.
what is
Okay.
AP? AP is a diameter, correct?
Right.
So that must mean AS is a tangent.
Oh,
Uh,
yes, yes.
does
Yeah,
that make
because
sense?
passes through the radius.
Yeah.
AS is right.
Yeah. So, okay, cool. Got it. If that was a little hard, then we'll do an easier problem. Actually, take a triangle ABC. H is the orthocenter. Um, let's call this HB, HC. Let's call this MB. Oh, that's all right. Now let me make another diagram. So meanwhile, think about this proof. Yeah, whatever I did here. You can watch this later on YouTube. It's called the feet of altitude HB and HC, and can call the midpoints MB and MC. So let's call X the intersection of MBMC and HBHC. Okay, yeah, and this is the orthocenter H. So what I want you to show that is AX is perpendicular to Euler line of. Did you get the question? Hello?
Yeah,
Yeah, yeah,
yeah.
okay.
Just repeat once
Can
again.
we just repeat once?
Yeah, I'll repeat. So X is the intersection of HBHC and MBMC. Oh, sorry. This is MB. Okay. Do you understand what the definition of X is?
Uh, MB is the midpoint.
Yeah, yeah. Sorry. I didn't say that. Okay.
Yeah, okay.
Really sorry.
And then MC is the midpoint.
Yeah, MB and MC are midpoints. I'm really sorry.
Okay. And
So
then
if you call
what is HB?
HB is the foot of altitude, HC is the foot of altitude from C.
Okay, okay. And H is the orthocenter of ABC.
Yeah, H is the orthocenter. So AX is perpendicular to OH is what you want to show. How will you proceed? Hmm. So first, we'll take the perpendicular from A to OH and let it meet OH at P some point. Okay. For now, let's remove X from the picture. Okay. So can you give me some cyclic quadrilaterals from here?
Yeah, AHCP,
A,
AHCHP, AHCHP,
AHC,
HP.
HB, you mean?
Yeah. No,
Yeah,
no.
no. I just
A H sub C H and P.
right. Okay. AHC, HP, and HB. I'll include HB also. Why not?
Then there are also many like
Uh,
A
now,
HC.
one minute. 1 minute, yeah. So I'll remove
Yeah.
H actually, not AHC, HBP. Does that make sense? They all lie on a circle with diameter AH.
Research.
Okay.
Yeah, makes sense. Yeah, that is
And
also
one more is
27.
AMB, MCP. They
Yeah.
lie on a circle with diameter AO. I'll just write
AO.
here.
Okay.
So now I'll
AMCP.
introduce
Okay.
X.
Yeah.
Or rather, if you notice, it's the intersection of circumcircles of AHBHC and AMBMC, right? It's the intersection of this circle, the circumcircle of this one, and the circumcircle of this one.
Yeah, right.
So what that means is P is the Miquel point of the four lines AHC, AMB, AH.
Four lines.
Four
Or a
lines, sorry,
triangle.
four lines.
Mickey point is defined for triangle or line.
No. Miquel point is defined for 4 lines also. So if you go back, yeah, Miquel point of 4 lines is here.
Oh, okay. Yeah, got it. Yeah, this
Um,
is like quadrilateral Mickle point.
yeah, this is a Miquel point of quadrilateral. I mean this figure here, entire figure, right? So if it lies on two circles, then it must lie on two more circles. What are the two other circles? If you introduce the point x, I mean you found two triangles from these 4 lines. The other two triangles are x MCHC and x MBHB. Correct? The triangle formed by this line, and this line.
Yes.
Do you understand what I'm saying or no? I'll just draw it here again.
Yeah.
So
Yeah,
this
but
is
that is
HB,
understood.
HC. Yeah, I'm just repeating what I just said. So what we have is P is a point which is the Miquel point of these 4 lines. Okay. So what I'm saying is P lies on this circle and P lies on this circle. Does that make sense? That's just because P is the equal point. Equal point of 4 lines. Are you able to follow? Hello.
Yes, yes,
Yeah,
it's
it's
clear.
clear. So, one thing is now MBMC HBHC is cyclic. Correct. This is just the 9-point circle. Yeah. Does that make sense?
Yeah,
Yeah.
yeah, but
Yeah.
because
Okay.
there are a
So
bunch of names.
sorry. Sorry. Can you repeat?
No, like
Uh,
you draw the 9-point circle in the previous time.
I don't hear you, unfortunately. So I'll just proceed. So applying radical axis theorem to this 9-point circle and these two circles in the bottom diagram. Okay, what do we get? MBHB is the radical axis, one radical axis. MCHC is the other radical axis. And PX is the third radical axis. These three are concurrent. So all that means is AXB are collinear. And does that make sense?
Yeah,
Huh?
pretty much.
Okay. So just a moment. Yeah, okay. Now I'll proceed to Steiner lines. So in general, Simpson line bisects the segment joining orthocenter in that point. Correct? If you take the Simpson line here.
What you said?
Yeah, Simpson line bisects this thing. It doesn't look like it,
Okay.
but yeah, I left it as an exercise to you. So a natural thing to introduce is a line parallel to the Simpson line passing through H. Right? This is just the dilation of Simpson line about P with a ratio 2. Okay, so if this
So like
point,
you're saying that
let's say
by
it's,
taking homothety centered at
yeah, homothety at P ratio 2.
and scale factor. Okay, yeah, got
Yeah,
it.
so H prime goes to H, and the Simpson line, let's call this L Simpson. This goes to something called the Steiner line. Okay, so I'll ask you a question. If this point is called E, now what is the image of E under this homothety? Homothety at P ratio 2.
Uh, Reflection of P across E.
Yeah, reflection of P about AC.
Yes.
So this point is, let's say, P sub B. This is the reflection of P about AC. Similarly, reflection of P about AB and BC.
Like the reflection of P across E will lie on
Side,
the through H. Uh,
Steiner line.
how does that?
Yeah, that's because of this dilation, right? Homothety at P ratio 2.
Oh,
And
okay, yeah,
see, because,
got it.
yeah, okay,
Because H prime
not
is
to
meant
be.
to H.
H prime is the midpoint of PH. H
Hmm.
prime also lies on the Simpson line of P. That's what I left as an exercise here. So this line
Yes, yes.
passing through H is called the Steiner line of P. I'll mark it in yellow. So the Steiner line of P passes through the reflection of P about sides of ABC. Correct? Because P sub A is the reflection of P over BC. And that's just the image of this point D. Similarly, P sub B is the image of point E under this dilation or homothety. Okay? So one thing to note is reflection of this Steiner line about any side passes through P. That's just the converse. Reflection of P about sides lies on Steiner line, and reflection of Steiner line about sides passes through P. Does that make sense? See, once again, it's really obvious because the reflection of this line about AC will pass through P because PB is a point on this line. Okay, I'll assume you got it. Move on. If you have any questions, please ask me. Hmm. So, given the Steiner line, you can construct P by reflecting about the sides. Okay. So now we'll go to Steiner line of four lines. So if you take 4 lines in general position, if you consider the Miquel point, let's say oh, um, yeah, let's call this point M. So the Steiner line of M with respect to any triangle over here will pass through the orthocenter of these triangles. Does that make sense? Just consider it lies on the circumcircle of all four triangles. So just consider any triangle. Yeah, let's name these points: A, B, C, D, E, F. The Steiner line of M with respect to this quadrangle or this four-line figure is called a complete quadrilateral. With respect to this figure is just the Steiner line of M with respect to any one of these triangles. So, for example, if you reflect M about any three sides, all four lines, am I making sense or?
Can you please repeat?
So, see, did you understand that the Steiner line of P is obtained by reflecting P about the sides and then joining them?
Yeah.
Yeah. So here, if you reflect M about all four sides, there are four lines here. If you reflect M about four lines, you get four new points. I'm sorry, the diagram seems to be very bad.
What is M?
M is the Miquel point of these four lines. M is here. So if you consider the Steiner line of M with respect to any one of these triangles or circles, you'll get a line which passes through the reflection of M about three sides. So let's say here, here, and here. Oh, yeah, okay. This is the
You are
Steiner line of
reflecting
M with respect.
across four lines.
Yeah, you reflect
Yeah,
across
got
all
it.
four lines,
Yeah,
and they'll be collinear. And this is the reflection across the fourth
okay.
line. Yeah, so this line is called the Steiner line of this complete quadrilateral. Okay, so since it's the Steiner line of
Yes.
M with respect to each of these triangles, each of the orthocenters of each of those triangles lies on this line, correct? The Steiner line passes through H.
What you said? What triangle?
Yeah, and there are many triangles. There are four triangles here, right? In this picture, disregard M for now. So there are four triangles. For example, AED is a triangle. And the Steiner line of M with respect to AED is this line L. Once again, this red line. This red line is called the Steiner line. The Steiner line passes through the orthocenter. So the orthocenter of each of these four triangles lies on this line. Does that make sense?
Yeah.
Yeah, okay, good. So the orthocenters of the four triangles formed by this setup are collinear. That's a nice result. Okay. Does that make sense? Hello. Hello.
Yes, it does.
Yeah. Okay. Good. Um. So this thing is from EGMO 2016. I'll leave that as an exercise. This is from 2017. Sorry, EGMO 2017 P6. Maybe you can just take a screenshot or just Google the problem. Now, just a moment. Yeah, I'll just show one result. So, does anybody know what a Gauss line of a quadrilateral is? Given a quadrilateral ABCD,
The midpoints of the diagonals.
yeah, just a moment. Let's call this F and E. So the Gauss line is the line joining midpoints of AC, BD, and EF, right? So I'll actually show you why these midpoints are collinear, and I'll show you that the Gauss line is perpendicular to the Steiner line. Again, Steiner line is the line containing the four orthocenters of these triangles. So for example, let's say H1 is here. H2 is here. So H1, H2 is the Steiner line of this quadrilateral, complete quadrilateral ABCDEF. So actually, if you notice something, H1 is the radical center on just a moment. Yeah. Consider the circles of diameter AC. This means circle with diameter AC, circle with diameter BD, and the circle with diameter AB. So, yeah, circle diameter AB looks like this. Circle with diameter BD passes through this point, say X. Circle with diameter BD, no, sorry. Circle with diameter BD passes through this point X, correct? Does that make sense?
Yes.
Yeah. The power of H1 with respect to circle with diameter BD is what? It's just H1X times H1B. That's because X lies on the circle with diameter BD. Right? Let me just draw the circle 1 second. So the circle power of H1 is H1X times H1B. And the power of H1 with respect to the circumcircle of, the circle diameter AC is H1Y times H1A, correct? Because again, Y lies on the circle diameter AC. Does that make sense? And these two values are equal, which means H1 lies on radical axis of AC and BD, the circles with diameter AC and BD, correct? Yeah, does that make sense? So what I'm just claiming is H1 lies on the radical axis of circles of diameter AC and diameter BD. If you speak up, it will be a little better.
Yes, yes.
Yeah. So what is the power of H1? Sorry, this is H1 with respect to circle of diameter BD. See, the circle of diameter BD passes through X because this angle is 90. And H1 is the orthocenter of ABF.
Oh, okay.
Correct?
Now I got it.
Yeah, H1 power of H1 is H1X times H1B. Similarly, power of H1 with respect to circle with diameter AC is H1Y times H1A. Now these two are equal because this quadrilateral is cyclic. Does that make sense?
Yes.
Yeah, so that means H1 lies on the radical axis of these two. Now similarly, you can show that H2 lies on the radical. Yeah, one more thing is O dot. The circle of diameter EF. If you consider this one, it passes through this point Z. Correct?
Yes.
So power of H1 with respect to circle of diameter EF is also equal to these two. So we'll call that. So it lies on the it lies on the radical axis. It has equal power with respect to circles of diameter AC, BD, and EF. Correct?
Yes.
Yeah. So we can use the same argument for H2 also. So I'll just write that down. H2 also same argument. H2 lies on H2 has equal power with respect to O dot AC. Circles of diameter AC, BD, and EF. Okay, and then similarly, if you take two other orthocenters H3 and H4, they also lie on the. They also have equal power with respect to these three circles. So what that means is these three circles are coaxial. That means they have a common radical axis, and the radical axis is the line H1, H2, H3, H4. Does that make sense?
Yeah.
So
So if they weren't coaxial, then there would be a radical center. That's why.
yeah. So if they were not coaxial, they would have some radical center. That radical, but then there are 4 points which have equal power.
Yes.
So that's not possible. In general, there's only 1 point which has equal power with respect to three circles. But then there are many points which have equal power with respect to three circles. That must mean these three circles are coaxial. So if these three circles are coaxial, one thing is three coaxial circles, they generally look like this. Sorry. I'm just drawing a diagram. So in general, they look like this, or if they intersect, they all pass through the same 2 points. For example, so these are examples of coaxial circles. And in general, coaxial circles, they have a radical axis in common. And in this case, the radical axis is the Steiner line. The Steiner line is the line H1, H2, H3, H4. And in the case of coaxial circles, the line joining centers is perpendicular to the radical axis, correct? So for coaxial circles, all three centers are collinear and the line joining centers is perpendicular to the radical axis. Does that make sense?
Yes.
Yeah, so what are the centers of these three circles? Circles of diameter AC, BD, and EF. The center of circle with diameter AC is what?
Their midpoint. AC
Midpoint
midpoint.
of AC. So the circle, the center of the circles with diameter AC, BD, and EF are the midpoints of AC, BD, and EF. And the line joining the centers is nothing but the Gauss line. Okay. So we have showed that the Gauss line is perpendicular to the Steiner line. So I'll give you one last problem as an exercise. This is quite. I mean, the first generalization we did. I'll just give that as an exercise. So the generalization of this problem. Yeah, this one right here. Just going to copy and paste. So once again, reminding you, A prime is the reflection of A over P, and X is the reflection of A prime over BC. So similarly, Y and Z are defined. So your goal is to show that O is the circumcenter of XYZ. And this problem is quite hard, so even if you don't solve it, don't worry. And if you solve it, you are probably very good. I'll end the session here. Yeah, if you want, you can stop the recording now. Any questions? I'll just stop recording.